Hi, thank you so much for watching. My name is Diego, and today we will review how to implement a physics-informed neural network in PyTorch. As always, you will find the final code in my GitHub, and the link will be in the description of this video. For this tutorial, please download this file. This is the reference solution that we will use to solve our problem. Okay, so what's exactly an inverse problem? Well, to answer that question, we have to go to what's a forward problem. Well, in a forward problem, you have a model and you use that model to get some data. Maybe you want to predict an outcome. And well, in an inverse problem, well, the opposite is true. So you will have some data and you will use that data to obtain a model. Well, kind of, because what you're actually obtaining is the model parameters. That's why this technique is also called parameter estimation. One of the most common examples of an inverse problem is training a neural network. So we know that a neural network follows the structure. And this is an unknown model that is parameterized by your weights and your bias for your n layers. So you will use your training data to estimate those parameters. Well, let's recall that a physics-informed neural network works with partial differential equations, and that partial differential equations are essentially models. And those models have parameters. We will call those parameters lambda. Well, in this kind of inverse problems, we'll have some data, which will be the solution of our partial differential equation, and we will use a physics-informed neural network to estimate our partial differential equation parameters. Okay, let's try to estimate the Burger's equation parameters. And well, in this case, this lambda 2 would be the diffusion coefficient, which if we were on the fluid mechanics field, then it would be related to the dynamic viscosity, which is related to the material. So let's assume we have some data from an unknown fluid. Well, then we could use this method to identify the material, which is pretty cool. Well, to do that, we have to rearrange our partial differential equation. We're changing the nomenclature a little bit here. We rearrange it to follow the structure set by the authors. But how do we actually solve this kind of problem? Well, let's recall that training a neural network, it's a case of an inverse problem. So we currently have the mathematical and computational tools required to estimate parameters inside of a neural network. So we will just place our lambda inside of our neural network. In other words, we will include our lambda 1 and lambda 2 as parameters of our neural network. And then we'll ask our optimizer to obtain the right value. Under what conditions? Well, let's recall that a physically informed neural network is a neural network that follows the rules set by a partial differential equation. Remember, we ask our neural network to approximate the solution of a partial differential equation. Since our neural network's function, we can obtain its derivatives. We can arrange those derivatives to follow the structure of the partial differential equation. We can call this arrangement F. And well, if our neural network approximates well to the solution of our partial differential equation, well, then F should be pretty close to 0. And that is the condition that we will try to enforce during the training process. How? Well, we will select a certain number of points inside our domain, and we will evaluate F. Remember that F contains lambda 1 and lambda 2. So if F goes to 0, it would mean that we will have found the right values of lambda. This is an inverse problem, so we actually have some data, which means that we can also evaluate the overall performance of our neural network. How? By comparing the real value against the output of our neural network. In other words, an inverse problem would be solved by minimizing two loss functions. The first one related to the partial differential equation, and the second one related to the overall performance of the algorithm. We will be using PyTorch as the machine learning framework, a matplotlib to visualize the data and also to plot our results, numpy to process our arrays, scipy to open the reference solution. Please remember that for this tutorial, you may need to download the reference solution that is on my GitHub. The link will be in the description of this video. Also, if you're running this code in Google Colab, please upload the reference solution to your Google Drive and use this line of code to be able to open it inside of this notebook. Okay, let's import and visualize the data. So we could go with data equals ip.io.loadmath. Here we should paste the directory of our reference solution. And well, if you're in Google Colab, just go to this little folder, navigate to where you save the reference solution, copy the path, and paste it here in the middle of your parentheses. Now let's open this container. We want to know the labels. So you can see that we have X for the spatial domain, U sol for the real solution, and T for the temporal domain. Let's skip those names. So it would be X equals data, word product of data, X, T, data, word product of data, T, the solution, word product of data, the U sol. So yeah, we're good. So now I've included some auxiliary functions to help us with the plots along this tutorial. So please feel free to pause the video, or if you want, you can download this code from my GitHub. So we would go with plot 3D and X, T, and U. Yeah, that would be the solution of our partial differential equation. So let's see how many points we currently have. So we have 256 points in X and 100 points in T. However, remember that in a forward problem, we needed to create a mesh, and this is not an exception. So to that, we would have X and T equals np.immesh of X and T. If we check the new dimension, we will see that we have a matrix, well, matrices of the combination of both dimensions. That's right. And well, however, remember that a neural network cannot handle a matrices, so we need to vectorize our input variables. To do that, we'll proceed with a column major flattening. And in the end, we will get two vectors of 25,000 points each one. And we will store both vectors into a single container. And to do that, we will go with x2 equals to, let's just stack both vectors. So it would be a horizontal stack of what? Of x, let's vectorize it with flatten. Let's keep only one of those dimensions. And let's do the same for the time. So, and if we in shape, we can see we have two vectors of 25,000 points each one, which is good. The last thing we need to do is to compute the lower and the upper bound. And now that we have a single container, it's pretty easy because the only thing we have to do is to take the first value for the lower bound and the last value for the upper bound. Let's bring those results to see. Yeah, you can see that our x goes from -1 to 1 and our time goes from 0 to 1. Okay, let's start with our training data. So remember that in this kind of problems, inverse problems, we just pick a certain number of points inside our domain and evaluate our partial differential equation and use those same points to evaluate our model performance. So we just need one group of data, which is quite different from than in a forward problem. Remember that in a forward problem, we had two groups of data, the collocation points at which we evaluated the partial differential equation, and also the boundary and initial conditions at which we will evaluate our model itself. So first, let's just pick certain number of points inside our domain. And to do that, first, let's see how many points we actually have. Total points will be the number of points in X times the number of points in T. You see that I'm picking the vectors. Then let's select NU points. Let's say we want 10,000 points. these total points will be the same number as this 25,600. If you see it. So yeah. Now let's create an index of random numbers. So to do that, we will have np that random the choice of what and the upper bound will be the total point. We want to select NU points and we don't want to replace them. Replace equals false. So we're good. Now let's create a new array that contains only these random points. And to do that, we will say xtrain to give the same names. Let's say xtrain NU equals x2 of what? Of our index. And we would have to do the same for utrain or the answer. But yeah, we haven't defined utrue, so we have to do that. In other words, we have to vectorize utrue. So to vectorize utrue, we would just have to say utrue equals usol. Remember that that's the name we gave it right here. So it's the solution of our progress equation. Usol that, let's flatten it. We want to do it a column major, and we will discard the last dimension. And so yeah, so that would be it. Let's hope it works. And yeah, it works. So now you see that we will have, let's print it. The total number of points that we will have will be, and we will select NU point. So the total number of points we had was 25,600, and we will pick a 10,000 points. And now we're ready to train our neural network. Well, before that, we may need to take all of these arrays to send out to our GPU or to our device, depending on what you're using. So send them to GPU. And to do that, let's go this folder as follows. Let's go use xtrain NU, which will be torch from an NumPy of what? Of xtrain NU. Yeah, we will transform that to a floating point, to a floating number, and then we will send them to our device. Yeah, we're making the tensor because remember, we need these tensors to work in PyTorch. So let's do the same for our solutions, which would be utrain NU equals, we're just transforming those variables. Yeah, to visualize data, let's do the same for the real solution. So it would be x2 of x2. Yeah, we're good. And also for utrue and also for the real answer, which would be utrue. So utrue equals from utrue. And we're good to go. Let's start with our neural network. Let's split our physics-informed neural network into two components, which would be the deep neural network itself and also its training process. So if we recall, a physics-informed neural network, it's a neural network that follows the rules set by a partial differential equation. And how do we make it follow those rules? It's through the loss function. So essentially, the only difference between a normal neural network and a physics-informed neural network is its training process. But why do we want to do this right now? Well, because remember that we will going to include our lambdas as parameters of our neural network. And so that way we define our neural network, we include our parameters, and then we train it. And that's what we're going to do. Okay, let's start initializing our parameters. Before we can include them into our neural network, we have to give them some kind of value. And that's what we're going to do right now. And the actual value is not that important. Well, it's important, but it's not that important because the optimizer will actually modify it while the neural network is training. So we know the real value. So lambda 1, the real value is 1. So let's make it 2. And lambda 2, it's 0.003. So let's make it almost 100 times bigger. So let's say 0.02. Yeah, as mentioned, this doesn't matter that much because the optimizer will modify these values. So once we have initialize our value, we can start defining our neural network. So let's call this class. This is in itself, it's a fully connected neural network. We just split it, but it's a fully connected neural network itself. So let's initialize it, which will be init, and we want to give it self and layers. The layers will be the array that will tell us how do we want to structure our neural network. Let's start with let's call our previous neural network, call our deep neural network. So to do that, let's say self dot DNN. You can give it whatever name you want. Equals we define it as DNN, so deep neural network of what? Of all layers. And once we do that, we want to send it to our device, which would be our GPU in this case. Now, once it's done, we can register our new parameters. To do that, we will first have to initialize our new parameters. Initialize. Well, actually, that would go first. Initialize our parameters. So we will call that self that lambda 1 equals, we want a tensor, remember, torch tensor of what? Lambda 1. We will require gradients because remember, we're going to differentiate these values. And once that's done, let's make it a floating point, float, and then we'll send them to our device. So let's do the same for lambda 2. That's how we include our parameters into our neural network. Yeah, and so then that is done. We will have to make it available to our optimizer, which we do, let's say, register lambda to optimize. And to do that, we will say self that lambda 1 equals, and then that parameter, that's how we make it a parameter itself, a meter of what? Of self of lambda 1. And we will do the same for our lambda 2. Yeah, and let's call our neural network after we have initialized our parameters. Yeah, we're good. Now register new parameters. And to do that, we will say self dot DNN register parameter self. What's wrong here? Something's wrong here. Okay, nothing. Okay, so self the DNN register parameter. The name we're going to give it is lambda 1, and what we would do want to register, it would be self of lambda 1. We will do the same for our lambda 2. And yeah, that would be it. Also, we need to define a loss function. So let's define a loss function. So let's say loss function. Well, the general loss function, we will have a specialized loss function, but the general loss function would be the mean squared error. So let's say self that loss function equals to NN. Remember, that's where we have all this kind of information. It's from PyTorch. We want the mean squared error loss, and we want the type of reduction. We want it we want the mean. Okay, so let's see what we have done here. Well, we defined our first loss function that computes the mean squared error of the output of our neural network against the real data. And that would be here, our first loss function. But remember that we also need a loss function related to our partial differential equation or related to f. But since f is parameterized by lambda, to define our loss PDE, which is right here, we start initializing lambda. And then we evaluate our partial differential equation. And to do that, we copy the value of x string, which could be the input variables. But remember that this is only a container that has both x and t. So yeah, we require the gradients because we're going to obtain its third derivative. Then we evaluate our neural network. So then we will see, first let's see what values we actually need. So this would be the Burger's equation. So we see we need the first derivative with respect to time, the first derivative with respect to x, and the second derivative with respect to x. So to do that, we go back here and to compute the first derivatives, we asked our program to differentiate u, which would be our neural network, against g. But remember that g has both values, x and t. So our first derivative would be with respect to x and t, and it will contain several derivatives inside of it. And the same holds for the second derivatives, but this times we will ask it to differentiate what? The first derivative, and we will ask it to differentiate it against the g. But remember, it's against, once again, it's x and t, so we will have a container that will have the derivatives respect to x and t and in all of the combinations. But how to obtain the values we actually need? So we needed the first derivative with respect to x, so we will take the container of the first derivatives and pick the first value. But why the first value? Because remember that when we input the data, we placed first x, then we place t. So to obtain t, we will pick the second value. And that's the same is true for the second derivative. Then we rearrange f. You can see that we have here lambda 1 and lambda 2. We know that f should go to 0, and that's, oh, I forgot to define f hat. Let's do it right now. But well, the thing is that if we want f to go to 0, these parameters will have to be optimized. So the program will find the right values of lambda 1 and lambda 2. And that's what we actually want. So what should be f hat? F hat, as mentioned, if n approximates to u, well, then f should be close to 0. So let's enforce that condition and do it right here. Okay, so let's say f hat equals a torch that zeros of what dimensions would we want the same numbers, number of items in next in u, only the first value, and then we want just one column, and then we will send this to device. And yeah, we should be good. Yeah, that's good. Let's go back here. So the overall loss function would be the loss function of the overall loss function and plus the loss function of the partial differential equation. So you can see that we just add them. This closer is to actually train our model. You can see that we define an optimizer. It's not defined yet. We will going to define it in a few minutes. We initialize our optimizer. We evaluate our loss function. We do the back propagation, and here just this code just to print the results. Also, we will add it. We add a section to evaluate or deep neural network in the X true, which would be the whole data set, and you will see it right here. For this value, we will obtain the relative error, not the the mean squared error. And yeah, so let's keep going. Okay, so let's create our physically informed neural network first. So PINN would be the name of our class, which was obtain of what? Of layers. But if I'm not, yeah, we haven't defined layers yet. The layers will contain the architecture. It's just an NP array. NP.array. And well, what the first value should be 2, since it's X and T. Then let's give it a certain number of hidden layers. In this case, we will use 8 hidden layers of 20 neurons per layer. So it's just type 28 times. Yeah, and the last value should be 1, since the only output that we're getting is the velocity. So yeah, that should work. Well, okay. Now let's isolate the parameters. We need this information to feed our optimizer. So let's say list of PINN. Remember that our deep neural network is inside of our PINN. Then we go parameters. Yeah, we're good. So now let's define the optimizer. The last time we used the Atom optimizer. So this time let's try the LBFGS optimizer. That's the one they used in the paper, just to try it. So to do that, we will go to torch.optim.lgbfgs. What do we want to optimize? We want to optimize params. The learning rate, let's set it to 1 to the -1. Yeah. Max iterations. Let's make it 20,000 iterations. Max evaluation, none. We don't have the value and we don't want to include it. The tolerance grad. This is like, remember that this training process is based on the gradient of the parameters. So if the parameters change is too small, then it would mean that we are stuck into a local minimum or that we have already got to the answer. So this kind of optimizer is like trying to make it efficient, the training process. So when you go to a place where you're stuck, the optimizer just quits. But we do not want this to interfere with our training process. So let's give it just a really small value. I'm not sure what's the machine epsilon for PyTorch, so let's just give it 1 to the -11. And also we have also something similar to the total change. So also let's give it 1 to the -11. The history size, let's give it 100 items. Line search FN, let's use this algorithm, which is a strong wealth. And yeah, we're good to go. Now, let's try to optimize our neural network to actually train it. So we'll go optimizer that step, and we want that's the reason why we included this closure function inside our physics informed neural network, and that should be enough. Let's see if it works. Yeah, so it's working. We see we have the relative error, and this is how the parameters are being estimated. You can see that how both values are attending to the real values and how the relative error in the testing data, so in the whole data set, is decreasing. So once the training process is completed, well, we can see that the relative error on the solution of a partial differential equation, it's 1.3%, which is pretty good. And also that our physics informed neural network did a really good job estimating our parameters. You can see that we have a 0.98 out of 1 for the first lambda, and also 0.0034 out of 31 for the lambda 2. However, as always, you can improve this model by modifying the learning rate, changing the optimizer, the number of iterations, changing the architecture of your neural network, and so on. And that would be all for that part. So let's review what we actually have. And this is the plot or our solution. Here in the black dots represent the training points, and I obtained this code from this repository, so please review it if you have time. It's pretty nice because this is quite similar of what Dr. Raisi showed in his paper. Okay, so what's the main difference between forward and inverse problems? It can be shown here. You can see that the points are taken inside our domain. Well, in the forward problem, we just take points inside our boundary and from our boundary and from our initial conditions. This is the Burger's equation solved as a forward mode. This code will be available in my GitHub too, so please review it if you have time. And then, well, this is our final plots. This would be the plots that we predicted with our model, and this would be the plots that we obtained using. This is the real data, and this is what we predicted, which is pretty close. So we can say that this physics-informed neural network did a really good job. And well, that would be all. Thank you so much for watching, and until the next time.